Uh, Dear students, after revision, let's move forward to understand about the reactivity towards the hydrogen. So, today let us understand the reactivity of alkali metals towards the hydrogen. You know, the alkali metals reacts with the dihydrogen at about 673 Kelvin temperature, lithium at around 1073 Kelvin temperature to forms the various hydrides. This 673 minus 273, that gives us 400 degree centigrade temperature. And when it comes to 1073, it simply gives us 800 Kelvin temperature, 800 degree centigrade temperature. So lithium takes almost double the temperature that the other metals takes to react with hydrogen and produces the hydrides. All the alkali metal hydrides are ionic solids with high melting points. So this is how the two moles or two molecules of metal reacts with one molecule of hydrogen to produce two hydride molecules, or you can say the two ionic molecules of hydrides. So this is how we can say, because mostly these hydrides are ionic, only the lithium hydrides have the covalent characters. We have already studied about these hydrides in detail into the chapter hydrogen. So we will not discuss more about these hydrides, but these hydrides are known as the salt-like or saline hydrides, or they are also called the ionic hydrides. Now we shall study about the reactivity towards halogen. The alkali metals readily react vigorously with halogens to form ionic halides like M plus and X minus. However, lithium halides are somewhat covalent in nature. So lithium halides are covalent in nature. It is possible because of the high polarizability or polarization capacity of lithium ion. We are well aware that lithium is small in size, or you can say the smallest among all alkalis. At the same time, this lithium has got plus one charge. So this charge is to radius, or charge is to volume ratio. Charge is to volume is high. This ratio is high for lithium, and that is why the polarizability of lithium is quite high. That is what we have studied into the Fajan's rule, that higher the charge is to size ratio or charge is to volume ratio, the more is the polarizability of the ion. So this is where the lithium is the most polarizing ion, or the polarizability of lithium is quite high as compared to the others. The distortion of electron cloud of the anion by the cation is called polarization. You see a very small cation, when it comes near to the anion, my dear students, this is having negative charge, this is having positive charge. What happens? The A very small cation comes near to the anion, my dear students. Then this charge or electron cloud of this anion get distorted. It goes like this. So somewhat the sharing character of these electrons which are present over here takes place between the cation and anion, and thus instead of maintaining the distance between the cation and anion, and then we have the electrostatic force of attraction between them, apart from that there must be some sharing character that takes place, and that particular sharing character is known as the polarization. So in the ionic compounds, this polarization takes place, and due to that the covalent character increases. The lithium ion is very small in size and has high tendency to distort the electron cloud around the negative halide ions, And since an ion with a large size can be easily distorted among the halides, and thus lithium iodide is the most covalent in nature. So my dear students, lithium is the smallest, Li plus 1 is the smallest alkali metal, and I minus is the biggest or largest halide ion. And that is why this has got the highest polarizability, and this has got the highest polarizing power, and it has got highest polarizability, and that is why this lithium iodide is the most covalent nature, or is having the most covalent nature among all the halides of our S block elements. Then my dear students, we want to study about the reducing nature. I have already informed you, or we have already studied, that reducing nature is determined by the electrode potential values. And when we look at the electrode potential values, our lithium has got the highest electrode potential, most negative electrode potential value, and that is why the reducing character of our lithium is the most. Now let us understand what are those factors that affect the reducing nature. The alkali metals are strong reducing agent. Metals are generally reducing agent, and alkali metals are the most metallic elements, and that is why they are strong reducing agent. Lithium being most powerful reducing agent, and sodium is the least powerful reducing agent. Please remember that lithium is the most powerful reducing agent, whereas sodium is the least powerful reducing agent among the alkali metals. This is the point you should remember if it is possible. The standard electrode potential, which is the measure of reducing power, represent the standard electrode potential, which is the measure of the reducing power, which represents the overall change. So if we move forward and understand M solid, that gives M gas. This is what it is known as the energy for this reaction is known as the sublimation enthalpy. Energy exchange during the process of M gas, that gives M plus, and electron, this is what it is known as the ionization enthalpy. And then this M plus gas ion, when it undergoes or when it goes to the water, it forms the M plus aqueous, and during that process the hydration takes place. We have seen that the hydrogen, the water molecule surrounds the ion, and that is why the hydration takes place, and this is how we understand the hydration enthalpy. So my dear students, when it comes to determine the electrode potential value of any element, we just consider these three things: sublimation, ionization, and hydration. The more is the hydration enthalpy that can overcome these two, and that is how the smallest ions, or the ions with the highest charge is to size or charge is to volume ratio, these type of ions are more prone, these type of ions are more possibility of having higher hydration enthalpy, and this is how we understand the highest hydration enthalpy for our lithium ion. So with the small size of ion, lithium has the highest hydration enthalpy, which accounts for its negative E0 value and its high reducing power. So my dear students, by taking this negative E0 value and high reducing power, we can say that lithium is the most most reducing in nature. Now let us understand these electrode potential values and their meaning with some of the example, my dear students. The E0 for Cl2 oblique Cl minus is plus, you can see this, plus 1.36. For I oblique I minus is plus 0.53. For silver oblique silver Ag is 0.79. For sodium oblique sodium is um, actually sodium plus oblique sodium, it should be, is minus 2.71 C, it is minus, and for lithium it is minus 3.04. So you can see that the E0 values for lithium is the most negative, and that is why it is most reducing in nature. So arrange the following species in order of their decreasing reducing strength. So first we will have to put the highest reducing strength, and then we will go for the lower one. So you can see that lithium has got most electronegative or most negative electrode potential value, and that is why it is most reducing in nature. Then we have sodium, then we have iodine, then we have silver, then we have chlorine. So this is how, my dear students, we understand about all the ions or all the we can arrange them in the order of decreasing reducing strength based on their electrode potential values. Let us study about the
Representing.
solution of these metals into the ammonia. So chaliye, let us study about the solution. The alkali metals dissolves in liquid ammonia, giving deep blue solution which are conducting in nature. So you can see that this is the ammonia, my dear students. This ammonia, we write it as X plus Y NH3, in which this metal gets dissolved, and then it forms the MNH3X. Please remember that this is the kind of the bond which is formed between the M and NH3X is the coordinate bond, and these ammonia are coordinated with the metal M, and then this electron also which are removed from the metal. This electron, not all the electrons, but out of X, only Y electron combines with the ammonia. And that is what it gives us the ammoniated electron. This is what it is known as the ammoniated electron. This is what it is known as the ammoniated electron, my dear students. So this is how we get an ammoniated electron, and that is why this solution becomes paramagnetic in nature, and this is what it gives us the blue color. So let me read it once again. The alkali metals dissolves in liquid ammonia, giving deep blue solution which are conducting in nature. Why they are conducting? Because these ammoniated electrons are available, and that is why they are conducting in nature. The blue color of solution is due to the ammoniated electron which absorbs the energy in the visible region of light and thus impart blue color to the solution. As it was explained that electron from the lower energy level goes to the higher energy level, and while coming back from the higher energy level to the lower energy level, it radiates the light. A light is being radiated, and that is what it imparts color. So this is how the color is being observed into the compound, and this here, this electron is actually the ammoniated electron. Now the color of the solution even changes as if it is kept for a longer time. The solution is paramagnetic in nature because there are unpaired electrons available which are ammoniated electron, and that is why it is paramagnetic in nature. Solution on standing, if you keep it for a longer time, solution on standing slowly liberate hydrogen resulting in the formation of amide. So this MNH2 which is formed is known as the amide. This M plus electrons available and NH3 which are ammoniated electron you can write, or you can just think of the electron and ammonia, and that is what it forms the metal amides MNH2, and hydrogen gas is released. So immediately this reaction does not take, immediately only this reaction takes place and we get a blue color solution. But this blue color solution is, if it is kept for a longer time, what happens, this blue color solution turns into or change its colors, and these metal amides are formed and hydrogen gas is released. So this AM what we have written is like AQ, which says aqueous solution, but here we write AM which means the solution in ammonia. So this is how, my dear students, we understand the ammoniated solution, and as we have aqueous solution, here these are the ammoniated solution, you can see that. So these are the solution in ammonia. In concentrated solution, the blue color changes to the bronze color and become diamagnetic. So slowly, if you keep it for a longer time, the blue color changes, the blue color turns to the bronze color, and the solution turns diamagnetic in nature. So this is how, my dear students, we understand about the solution. Now we want to study about the uses of these metals which are known as the alkali metals. Let us study about the uses of the alkali metal. Lithium is used to make useful alloys. Example, lithium with lead to make white metal. This white metal is used to make bearings for the motors of engines. So lithium makes white metal, and white metal is used to make the bearings of the motor engines. Lithium with aluminum makes an alloy, and that is what it is, the alloy used for the aircraft. Lithium with magnesium make an alloy, and this metal or this alloy is used into making the armor plates. Armor plates means the guns and missiles and tanks and all this. They requires the various plates. These plates are made by the alloy of the lithium and magnesium. Then, my dear students, lithium is used in the thermonuclear reactions. So, lithium is used in the thermonuclear reaction. Thermonuclear reaction is the type of reaction where the nuclear energy is used to produce heat, and from this heat, the electricity is produced. Lithium is used to make electrochemical cells also. So electrochemical cells are the devices that produces electricity or that converts the chemical energy into the electrical energy. So lithium is used into producing the electrochemical cells. My dear students, it's the edge, or it is now the time period for the various mobiles, and in mobiles we get battery. This battery is majorly the lithium battery. So these type of cells which are made from lithium, we have been using them in our daily life in the mobile. Now, my dear students, we want to study about the sodium. So there are various uses of sodium. Sodium is used to make sodium lead alloy. This sodium lead alloy needed to make PbEt4, that is a triethionide lead, or PbMe2, that is a trimethyl lead. This Et means ethyl group C2H5, and Me means methyl group CH3. These organo-lead compounds were earlier used as an anti-knock additives to petrol, but nowadays the vehicles use lead-free petrol. So like previously, the petrol was added with these compounds which are known as the PbEt4 or PbMe4, and these compounds are used as an anti-knock agents. This reduces the noise into the engine of the vehicles, but this lead which is produced into the smoke due to this compound is very harmful, and that is why nowadays we do not use the petrol added with PbEt4 or PbMe4, and we nowadays use the lead free petrol. But earlier the compounds of lead, PbEt4 and PbMe4, were used as an anti-knocking agents. Lithium sodium metal is used as a coolant in the fast breeder nuclear reactors. So if you have nuclear reactor where the nuclear energy is converted into electrical energy, this kind of to cool the nuclear reactor, this lithium sodium alloy is used as a coolant. Now potassium has a vital role in the biological system. You will study about the sodium potassium pump in biology. Potassium chloride is used as a fertilizer. We know that NPK, if you are a farmer, then these three things are needed into our fertilizer: nitrogen, potassium, and phosphorus. So these NPK are needed for the various fertilizers, and that is why potassium is one of them, and that is why it is used into the fertilizers. Potassium hydroxide is used in the manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. So there is a compound of potassium which is known as the potassium hydroxide, KOH. This potassium hydroxide is used in the production of the soft soap, which we call it them as a liquid soap sometime, and it is also used as an excellent absorber of the carbon dioxide gas. And then we have the cesium. Cesium is used in the devising of the photoelectric cell. These are the cells which are also known as the solar cell, and that is how, using the solar cell, we convert the solar energy into the electrical energy. This is possible due to the very small energy needed to release the electron from cesium, and that is why we can say that cesium has got very small ionization energy. And this is how, my dear students, we understand about the very small ionization energy of the cesium. Then, my dear students, we have the next question to do, that is general characteristics of the compounds of the alkali metal. So let us look into the various general characteristics of the alkali metals. All the common compounds of the alkali metals are generally ionic in nature. So the compounds of alkali metals are generally ionic in nature. Only the lithium compounds have covalent character. General characteristics of some of their compounds are discussed. So let us discuss the various characteristics. First, their oxides and hydrides. So on combustion in excess of air, lithium forms oxides Li2O plus some peroxide Li2O2. So lithium forms oxides Li2O and some of the other oxides like Li2O2 is also formed by lithium. Then we have the sodium forms the peroxide Na2O2 and some superoxides also, whereas potassium, rubidium and cesium form superoxides MO2. Thus we can conclude that under appropriate condition, pure compounds oxide M2O, peroxide M2O2 and superoxide MO2 are formed, and this may be prepared under the proper or required conditions. The increasing stability of peroxide or superoxide as the size of the metal increases is due to the stabilization of the large anions by larger cation through lattice energy effects. So this is the important points, my dear students. If you look into the group number 1, we have lithium, sodium, potassium, rubidium, cesium and francium. If you go down the group, the size increases, the size become bigger and bigger. And if you look into the ions O minus 2, then if you look into the ion O minus 1, and if you look into the ion O2 minus 1, then you will realize that if you go from this to this, even the size increases. So the bigger sized ions are accommodated by the bigger ions. So these are the ions which are bigger in size, and that is why they make the superoxides. Sodium makes the peroxide and lithium mostly makes the oxide. So as we go down the group, the size of the ions increases. As the size of the ion increases, they make the compounds with the more sized ions. And as far as oxides are concerned, there are three types of oxides: oxide, peroxide and superoxides, and the bigger ions accommodate bigger superoxide, and that is why potassium, rubidium and cesium mostly forms the superoxides, and that is what they do it by the effect of their lattice energy. So when they combine with each other, if both ions are bigger in size, the lattice energy is good enough to make the compound more stable, and that is why using this lattice energy effect, this potassium, rubidium and cesium forms the superoxide which are stable. Sodium, if forms the superoxide, it is not so stable as the potassium, rubidium or cesium superoxides, and the peroxide formed by lithium is not so stable as the peroxide formed by sodium. But um, these all elements, one or the other way, they forms the various types of oxides. These oxides are easily hydrolyzed by water to form their hydroxides. So these oxides, when they are added to water, they form hydroxides, and according to the following reaction, you can see that they form the hydroxide. These 2M plus 2M plus and plus 2OH minus, which simply gives us 2MOH. Please remember. So actually it is 2MOH written here. So when MO2, that is oxide, reacts with water, it produces directly hydroxide. If peroxide reacts with water, it produces the hydroxide plus hydrogen peroxides. And if superoxide reacts with water, it produces hydroxide, hydrogen peroxide and oxygen. Please remember, this is even very important if you understand, my dear students, that when our oxide reacts with water, it produces hydroxides. When our peroxide reacts with water, it produces the hydroxide plus hydrogen peroxide. When our oxide reacts with water, it produces the hydroxides, hydrogen peroxide as well as oxygen. The oxides and the peroxides are colorless when pure, but superoxides superoxides are generally found a little bit colorful. So, but superoxides are yellow or orange in color. So, the superoxides of potassium, rubidium or cesium, they are either yellow in color or orange in color. Please remember that the superoxides of alkali metals are yellow in color. The superoxides are also paramagnetic in nature. The sodium peroxide is widely used as an oxidizing agent in organic chemistry. First of all, let us look at this, that these superoxides are also paramagnetic in nature. So they are paramagnetic and they have unpaired electron present into them. And when we look to the next, we have even seen into the chemical bonding, there's O2 minus 1 ion is paramagnetic in nature and it has got unpaired electrons by the molecular orbital theory. And this sodium peroxide is used for the oxidation of the other substances. So it is a very good oxidizing agent. Now the question, why KO2 is paramagnetic? So we have just seen, or if you write the electronic configuration for the O2 minus according to the MO theory, molecular orbital theory, you will come to know that uh, O2 minus is a paramagnetic in nature, and that is why KO2 is also paramagnetic in nature. The superoxide ion O2 minus is paramagnetic because of the unpaired electron present into pi star 2p molecular orbital, and that is why KO2 is also paramagnetic in nature. The hydroxide which are obtained by the reaction of the oxide with water are white crystalline solids. So all the hydroxide, be it lithium, sodium, potassium, rubidium, cesium or francium hydroxide, these all are solid crystals. They are water soluble and they have white color. Please remember, the alkali metals, hydroxides are the strongest of all bases. So alkali metal hydroxides are the strongest base among all the bases available, and they dissolve freely in water with evolution of much heat on the account of the intense hydration. So these alkali metal hydroxides, when they are added to water, the heat is produced, or the dissolution of these hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, is an exothermic process. The heat is released during this process, and this is what it happens due to the very high hydration of the small alkali metal ions. So this is how, my dear students, we study about the various characteristics of these ions. Then we study about the halide ions. So please let us study about the halides of these alkali metals. When we look into that, the alkali metal halides, that is MX, are all high melting colorless crystalline solids. They can be prepared by the reaction of the appropriate oxides. So my dear students, these metals also forms the halides. They form the fluoride, chloride, bromide and iodide, and these halides can be prepared by the reaction of their metal oxides with appropriate compound. They can also be prepared by the metal hydroxides with the appropriate compound, or they can be prepared from the metal carbonates also. So let us see the reactions. See, from metal halide, see, if hydrogen halide reacts with the metal oxide, it produces metal halide. When hydrogen halide reacts with the hydroxide, it produces metal halide. When hydrogen halide is allowed to react with metal carbonate, we get metal halides. So hydrogen halide, when reacts with the alkali metal oxide, alkali metal hydroxides or alkali metal carbonate, they produces the metal halides. So these metal halides can be produced from the hydrogen halides. These halides have negative or high negative enthalpies of formation. So when they are produced, the heat is uh, produced. The formation of enthalpy of formation value for fluoride become less and less negative as we go down the group. So the possibility of formation of fluoride decreases as we go down the group, and that is why the enthalpy of formation also decreases and go less and less negative, or less and less energy is produced, and that is why the bond between fluoride and the alkali metal ion is not so strong, because fluoride is very small in size, and as we go down the group, the size increases, and as the size increases, the bond become less and less stronger, because there is a wide difference into the size of these ions, and as the size is not same, or not compatible, that is the word I would like to use, as the size is not compatible, as the size is not compatible, they do not accommodate the small ions, um, the small fluoride ion is not properly accommodated by the bigger ions, and that is why the bond between these ions are not so strong. So we can say that the rubidium or cesium fluorides are not so stable as the sodium fluorides or potassium fluorides can be stable. The formation of enthalpy of formation value for chloride, bromides and iodides become more and more negative as we go down the group. So if we go down the group, these bigger ions like chloride, fluorides and bromides, they are easily accommodated by the bigger ions like uh, sodium, potassium, rubidium, cesium, and that is why the enthalpy of formation is increases as we go down the group. A given metal enthalpy of formation always become less negative from fluoride to iodides. So for any metal, if we make the or if we understand the enthalpy of formation, so for any metal the highest enthalpy of formation is with the fluoride and lowest enthalpy of formation is with the iodide. So the all the iodides of these metals, they are not so strong or they are not so ionic in nature, but all the fluorides, they have the strongest bond and they are ionic in nature. The melting and boiling point always follow the trend that fluorides will have the highest melting point and iodides will have the lowest melting point. Then after fluorides, the higher melting point is with chloride, then with bromide, and iodide will have the smallest melting point. All these halides are soluble in water. Please remember that all these halides which are formed by alkali metals, they are soluble in water. The low solubility of lithium fluoride in water is due to the high lattice enthalpy. Now you see lithium is a very small ion and our fluorine is also a very small ion. So they have the high charge is to size ratio, and as this charge is to size ratio is very high, they they have the very high lattice enthalpy, they make a very strong bond, or the electrostatic force of attraction is very high, and that is why they have got very high lattice enthalpy. And due to this very high lattice enthalpy, their hydration energy does not overcome this lattice enthalpy because they form very strong bond and their lattice enthalpy is very high. And due to that, they are not able to dissolve into the water. So please remember that lithium fluoride is not possible to be dissolved into the water. Low solubility of cesium iodide. You know, cesium iodide. Now they are compatible with each other, and that is why they have same size. As they have same size, they and their these ions, cesium ions and iodide ions, both are bigger in size. And as they have the very small charge into size ratio, because they are bigger in size, the size is very high for these ions, my dear students. The size is big, and as they have big size or they have charge is to size ratio is very small, we can say they have smaller hydration enthalpy, and that is why their lattice enthalpy is not overcome by the hydrogen enthalpy, and that is why they can not be dissolved into the water. So please remember, my dear students, that the lithium fluoride and the cesium iodide are not water soluble. Other halides of lithium are soluble in ethanol, acetone, and ethyl acetate. So lithium halides, they are covalent in nature, and that is why they can be dissolved into the organic solvents like ethanol, acetone, and ethyl acetate. Please remember, my dear students. Now we want to study about the salts of oxoacids. So before we start studying about the salts of oxoacid, my dear students, let me give you the definition of the oxoacid. So oxoacids are those compounds in which acidic proton is on a hydroxyl group with an oxo group attached to the same atom. For example, if we have carbonic acid, then CO3 minus 2 is known as the oxo anion. Same way SO4 minus 2 is known as the oxo anion. Same way NO3 minus is known as the oxoanion. Same way HCO3 minus are known as the oxoanion. So if an element make carbonate or sulfate or nitrate or hydrogen carbonate with hydrogen, then these kind of compounds are known as the oxoanions. You can see that the hydrogen which are produced by such acids are not directly bonded to the central atom, but they are just bonded to the hydrogen, they are just bonded to the oxygen as an OH molecule, and that is why you can say that H2CO3 is nothing but COOH twice. SO4 minus 2 is nothing but SO2 OH twice. So this OH twice, this hydrogen are bonded directly to the oxygen, and that is why such ions are known as the oxo anions, and such acid produced are known as the oxoacids. So my dear students, today let us stop our discussion over here and let's move for the revision. I hope you have enjoyed the class, and if you have any doubt, you can ask me.